If you take a strong electrolyte, the blue one is my strong electrolyte and the green one is my weak electrolyte. This we just saw. Strong electrolyte, for example KCl, and weak is like acetic acid. So for a strong electrolyte, if you see, here we are increasing dilution, here we are making it more concentrated. So if you go from right to left, we are diluting the whole solution. That means if you see going from left to right, when you're diluting, the lambda M increasing, right? So molar conductivity increase slowly on dilution. This dilution is in this path. And for that he gave an equation that is lambda M at beginning point is nothing but this is value at infinite dilation minus a c to the power 1 by 2. C is a constant, or A is a constant, and C is the concentration. And the value of A depends on the solvent actually, right? For example, if you see, it depends on the pair. For example, NaCl and KCl will have same value of A. It depends on the number of ions it produces actually. Okay. For example, NaCl, KCl will produce 2 ions each. CaCl2 will produce 1 ion of 2 positive charge and 2 ions of 1 negative charge, right? MgCl2 will be doing the same thing. So they'll have same value of A. MgSO4 will produce 1 ion of plus 2 charge and this ion of negative charge. Calcium sulfate also will produce 1 ion of plus 2 charge, Ca plus 2 and SO4 minus 2. So this will have same, these two will have same value of A, this two will have same value of A, this will have same value of A. This A depends on my solvent actually, correct? I mean the number of the types of cations and anions it produced. So all the electrolytes, they'll have same of particular type will have same value of A, correct? But if we talk about the variation of molar conductivity of a weak electrolyte in this case, that is not a linear function. You see, this is not a linear function, this is a linear function, correct? This is not a linear function. See, it goes something like this. It's not a linear function, correct? So the evaluation of this molar conductivity at infinite dilution, the moment you keep diluting, you want to find the value of conductivity here, molar conductivity here. It's not very certain. And for this, he proposed one more law. He proposed that at infinite dilution, at infinite dilution, and this is for weak electrolytes, or in fact for all actually, this is for all. At infinite dilution, the cations and anions, since it is infinitely dilute, they move independently of each other. They move independently of each other in the solution. And this idea was discovered by Kohlrausch in 1875. In 1875, he thought of this idea. To prove this, what he did was he measured the molar conductivities of strong electrolytes. Please note, he took strong electrolytes. And since I am talking about infinite dilution, he took strong electrolytes at infinite dilution. Right? He did that, and let's see what the result was. So he did the research and he found that the molar conductivity for the pairs of salt having a common ion is approximately same. At this lambda M the difference in lambda m, actually the difference in lambda m for pairs of salt, and that pairs of salt should have one common, is same, approx same. For example, he has taken Ki and Nai pair, found the difference. He took KBr and NaBr pair, he found a difference. He took KCl, NaCl, KCl NaCl pair, he found a difference. He took KNO3 NaNO3 pair, he found a difference, and he found a difference of lambda. So he found that for Ki-NaI pair, for all these actually, the value came out to be approximately 23.4 Siemens centimeter square per mole. What you observed is, that means if you see here, if you remove II, you get K minus Na. You remove Br, because I'm subtracting, you get K minus Na. You remove Cl, you get K minus Na. NO3 remove, we get K minus Na. So with that, he concluded that at infinite dilution, the cations and anions contribute independently to the molar conductivities. Please note, the conclusion he gave was from this experiment was that, again, since everything is happening at infinite dilution, because at infinite dilution you can at least find the molar conductivity of a strong electrolyte, but for a weak electrolyte you can't find, right? Because they hardly dissociate. So at infinite dilution, my cations and anions they contribute independently to molar conductivity of electrolyte. So that was he concluded. Correct? He took other pair also. For example, one pair he took was NaBr and NaCl, and he took KBr and KCl. So if you see this pair now, and he found the lambda m and lambda m, you see here Na gets cancelled, here Kk get cancelled, right? So in both the case, the lambda came out to be 1.8 Siemens centimeter square per mole. Right. So thus he told that the lambda m, that is my molar conductivity, can be expressed as sum of molar conductivities of individuals ions of electrolytes. Because since they are contributing independently, I can say that lambda m can easily be replaced as nothing but sum of the molar conductivities of individual electrolytes. And this is nothing but Colruyt's law of independent migration of ion. Colruyt's law of independent migration of ions. Correct? That means, for example, I have, let's suppose, NaCl at an infinite dilution, right? If I want to find the limiting molar conductivity of NaCl, so that will be nothing but limiting molar conductivity, I'll put it not here, of NaCl will be nothing but limiting molar conductivity of Na plus limiting molar conductivity of NaCl minus. Just add these two, you get the value. Correct? But for example, you have CaCl2. CaCl2. So in that case, you get two chlorine ions. So it will be Ca2 plus 2 into limiting molar conductivity of chlorine, because you get two chlorine ions and one calcium ion when CaCl2 dissociate. So there is a general rule actually. Let me write that general rule. The general rule is that, so if I have an electrolyte that on dissociation gives X cations and Y anions, let's suppose. So the limiting molar conductivity of the whole solution will be nothing but X into lambda of cation plus Y into molar conductivity of anion. Correct. For example, MgCl2, it will give you 1 Mg plus 1 cation and 2 anion, 2 chlorine. So it will be lambda of Mg plus 2 of lambda chlorine. It's a general rule actually. So it gives X cations and Y anions. Then X into the molar conductivity of cations, because you are getting X number of cations, and plus Y into molar conductivity of anion, because you are getting Y number of anions. And this is the molar conductivities, the limiting molar conductivities actually for cations and anions, the popular values at 298 Kelvin. For H plus, this is the value 349 Siemens centimeter square per mole. For Na plus, 50.1 centimeter square Siemens centimeter square per mole. For K plus, 73.5 Siemens centimeter square per mole. Similarly for Ca plus, 11.119 Siemens centimeter square per mole. Similarly for OH minus, we have this value 199.1 Siemens centimeter square per mole. Similarly for Br minus, I have this value. If you see, for CS3CO minus, we have this value. It depends on the size. If you see, CS3CO minus is big in size. Since the anion is this ion is bulky, the conductivity is less. H plus is very nimble, very small in size. So in this case, if you see, conductivity is almost maximum here. Correct? So it all depends on the size of the ion. Now let's see the Colrosh law for the weak electrolytes. So as I've told, this Colrosh law of this independent migration of ions, this was used for weak electrolytes generally, because for weak electrolytes it's very difficult to find the molar conductivity at a very high dilution, because at that high dilution the degree of dissociation is very high, right? And it's a very uncertain value. So the molar conductivity at infinite dilution, so let's suppose it's almost zero, concentration is almost zero. So in that case, the dissociation of is almost 1. That is, let's suppose I take a weak electrolyte. Right, so this is, I'm diluting it. And this is my molar conductivity. Correct. So I'm at infinite dilution, this alpha is almost 1, because this will be, let's suppose C, this becomes 0, 0 at t is equal to 0, this becomes C alpha, this is C into, this becomes C into 1 minus alpha, this becomes C alpha, and this becomes C alpha, right? This you have seen in the equilibrium classes, this kind of equations. So at infinite dilution, C is almost 0 and alpha is almost 1. So but at such low concentration, we have told that conductivity of solution is very, very low and it cannot be measured accurately. So we came up with this, Colrosh came up with this law of independent migration, which says that at any given concentration, I mean, you can just add at infinite dilution, the molar conductivity of this solution is nothing but the molar conductivity of individual ions. Correct. Now, at any given concentration, let's assume we are coming with the new formula now. At any given concentration, if alpha is my degree of dissociation, correct? So my alpha, I can easily approximate alpha to be the ratio of molar conductivities at that alpha can be this value by this value, or let's not confuse, let's make it lambda m by lambda m naught. Okay, lambda m naught is nothing but my molar conductivity at infinite dilution, right, where C is almost equal to 0, and this is my molar conductivity at in time, and C is equal to C, some value. So I'm saying dissociation is almost equal to the molar conductivity at a given concentration divided by molar conductivity at infinite dilution. So if you want to find this K, equilibrium constant is nothing but Cl, equilibrium concentration of CH3CO minus concentration of H plus by concentration of CH3COH. This becomes C alpha, C into 1 minus alpha. Cancel. It becomes C alpha square 1 minus alpha. Just put the value of alpha. Alpha is nothing but lambda m by lambda m naught. C into lambda m by lambda m naught by 1 minus lambda m by lambda m naught. This value you will get. If you solve it, you get C into lambda m square by lambda m naught by lambda. This is what you will get the value of equilibrium constant. You can find the value of equilibrium constant using the value of lambda m naught and lambda m, that is molar conductivity at infinite dilution and molar conductivity at that point of time where you want to find the value of K. So let's see the application of Colruyt's law we have just seen. First thing is that it is used to find the value of molar conductivity at infinite dilution for a weak electrolytes. At infinite dilution. Correct? For example, if I want to find the molar conductivity of CH3COH at infinite dilution, that will be nothing but molar conductivity of CH3CO minus at infinite dilution plus molar conductivity of H plus at infinite dilution. These values you can actually get in some textbook. That is the first application. The second application, it is used to find the dissociation constant alpha. As I told, alpha is almost equal to lambda m by lambda m naught. Correct? Second thing, once I have alpha, I can easily find the equilibrium constant C alpha square by 1 minus alpha, at least for this equation. Correct? So I can find the dissociation constant, I can find the equilibrium constant, I can find the value of molar conductivity for a